Europa was supposed to be simple. A frozen moon. A dead world. Just ice orbiting Jupiter in silence. But the more we studied it, the worse it got. Beneath that cracked surface isn't rock. It's an ocean deeper than all of Earth's combined. And above it, radiation so intense it would kill an unprotected human in minutes. If life exists down there, it has been sealed off for billions of years. And the terrifying part isn't what we might find. It's that once we break through that ice, we may not be able to control the terror we might unleash. Europa was never meant to be terrifying. For decades after its discovery in 1610, it was just one of Jupiter's moons, a bright speck of light moving in predictable rhythm around a gas giant. Even when spacecraft first sent back close-up images, it didn't look threatening. It looked smooth, pale, scarred with long reddish cracks, yes, but calm, silent. It was supposed to be a frozen relic. And then the data came in. When NASA's Galileo spacecraft entered orbit around Jupiter in the 1990s, it wasn't looking for horror. It was studying magnetospheres, gravitational fields, plasma interactions. But Europa kept giving strange readings. The moon's magnetic field wasn't behaving the way it should if it were just solid ice and rock. Something beneath the surface was conducting electricity. And there are not many materials that conduct electricity that well. Liquid saltwater does. That was the moment Europa stopped being simple. Europa is about 3,100 kilometers in diameter, slightly smaller than Earth's moon. But unlike our moon, its surface is almost completely smooth compared to most rocky bodies in the solar system. There are very few impact craters, which means the surface is young. It has been resurfaced, reshaped, renewed. Something is moving beneath it. That cracked surface, those chaotic patterns of broken ice slabs that look like frozen puzzle pieces, are not static scars. They are signs of motion. Tidal flexing from Jupiter's immense gravity stretches Europa as it orbits. The moon doesn't travel in a perfect circle. Its orbit is slightly elliptical. That means Jupiter's gravitational pull changes subtly during each orbit. And that change squeezes Europa. Literally, the entire moon flexes. It rises and falls by up to 30 meters with each orbit. Imagine the crust of an entire world bending like that every few days. That constant flexing generates heat through friction inside the moon's interior. That heat keeps something liquid. The current consensus, based on gravitational modeling and magnetic field data, is that beneath Europa's ice shell lies a global ocean, perhaps 60 to 150 kilometers deep. Let that sink in. Earth's average ocean depth is about 3.7 kilometers. The deepest trench on Earth, the Mariana Trench, is roughly 11 kilometers deep. Europa's ocean may be more than 10 times deeper than that. And it's global. There are no continents, no shorelines, just a planet-sized ocean sealed beneath ice. And that alone would be fascinating. But then there's Jupiter. Europa does not orbit a quiet planet. Jupiter is a radiation machine. Its magnetic field is the most powerful of any planet in the solar system. It traps charged particles and accelerates them to enormous energies. That radiation belt bathes Europa constantly. The surface radiation dose on Europa is estimated to be about 5.4 sieverts per day. For context, a dose of 4 to 5 sieverts delivered over a short period is typically lethal to humans without medical intervention. On Europa, you would receive that in less than 24 hours. Some estimates suggest that an unshielded human would receive a lethal dose in just minutes. That's why the thumbnail says we can't go here. Not because it's far, not because it's cold, but because Jupiter turns its moon into a radiation furnace. Any spacecraft that orbits Europa for long periods must be heavily shielded. Electronics degrade, sensors fail, materials accumulate damage. That's one reason the upcoming Europa Clipper mission is designed to perform multiple flybys rather than settle into long-term orbit around Europa itself. Even our machines struggle there. And yet beneath that radiation-blasted crust may be an ocean that has been isolated for billions of years. This is where it gets uncomfortable. On Earth, Life thrives around hydrothermal vents deep in our oceans, environments with no sunlight. Microbes use chemical energy from interactions between water and hot rock. It's called chemosynthesis. Entire ecosystems exist independent of sunlight. If Europa has a rocky core, and models suggest it does, then tidal heating could generate hydrothermal activity on its ocean floor. Water touching warm rock, chemical gradients, energy sources, potentially everything you need for microbial life. Some researchers have even proposed that Europa's ocean may have twice as much water as all of Earth's oceans combined. That means if life began there, even in simple microbial form, it has had billions of years to evolve in isolation. Total darkness, high pressure, no surface contact, no meteorite exchange, no contamination, an independent biosphere. Think about that. If Europa has life, it would not share ancestry with life on Earth. It would represent a second genesis, a completely separate origin of life in the same solar system. That would mean life is not rare. It would mean biology is not a miracle that happened once. It would mean the universe may be biologically fertile. And that possibility is exhilarating. But it is also terrifying. Because to confirm it, we would need to break through the ice. Europa's ice shell is estimated to be between 15 and 25 kilometers thick, though some models allow for thinner regions. Hubble observations have hinted at possible water vapor plumes erupting from cracks in the ice, similar to what we see on Saturn's moon Enceladus. If those plumes are confirmed, they may allow us to sample ocean material without drilling. But if we ever attempt a direct probe, a lander, a cryobot melting through kilometers of ice, we face a different kind of danger. Contamination. Earth is full of microbes. Even with sterilization protocols, spacecraft carry trace biological material. If we send a probe into Europa's ocean and introduce terrestrial microbes, we risk seeding a second biosphere with Earth life. We might overwrite it. Or worse, we might alter it irreversibly. Planetary protection protocols are strict for this reason. Europa is categorized as a high-priority target for contamination control. Any mission attempting subsurface exploration would require extreme sterilization standards. But here's the paradox. If we are too cautious, we may never explore. If we are not cautious enough, we may destroy what we seek to discover. And then there's another angle. What if life exists down there, but not in the way we expect? Europa's ocean is under immense pressure. The chemistry may include high concentrations of salts, sulfur compounds, oxidants created by radiation interacting with surface ice and transported downward through cracks. The environment would be alien. If organisms exist, they would be adapted to darkness, pressure, cold, and perhaps chemical compositions unlike anything on Earth. We often imagine exploration as a one-way revelation. We discover, we learn, we return safely. But on Europa, the equation is different. If we breach that ice and open a pathway between the surface and the ocean, we are altering a system that has been closed for billions of years. Closed systems evolve uniquely. Closed systems are fragile. Europa's ice shell acts as a shield, protecting the ocean from radiation, meteorite bombardment, and external influence. That isolation is precisely what makes it scientifically priceless. It's also what makes it dangerous to disturb. Because we don't know how its ecosystem, if it exists, would respond to change. Even sampling surface material is not trivial. Radiation continuously alters the chemistry of Europa's ice. Oxidants are produced at the surface and may migrate downward, potentially providing chemical energy to the ocean below. The entire moon may function as a slow, global chemical engine. Break that engine carelessly, and we interfere with processes that have run uninterrupted for geological timescales. And yet humanity is preparing to go. Europa Clipper will launch to study the moon in detail, mapping its ice thickness, analyzing its chemistry, searching for active plumes. It will not land, not yet. But the next generation might. Because curiosity is relentless. And Europa is too compelling to ignore. A global ocean, a radiation-blasted crust, a flexing ice shell, a possible second origin of life. It forces a question that is bigger than Europa itself. If life can exist there beneath ice, without sunlight in isolation, then what does that say about the universe? It means habitable environments may be far more common than we thought. It means the scariest thing about Europa isn't a monster beneath the ice. It's that it might be alive. And if it is, we are standing at the edge of a decision. To explore or not. To drill or not. To risk contamination or remain ignorant. Europa is not what we think it is. It's not just ice. It's not just a moon. It may be a sealed ocean world, older, deeper, and more biologically significant than anything else we've ever encountered beyond Earth. And if we go there, we must be prepared for the possibility that we are not alone, not in the galaxy, not even in our own solar system. But that realization comes with consequences. Because discovering life is one thing. Interacting with it is another entirely. Because once you accept that Europa may not be a frozen wasteland but a sealed ocean world, the question changes. It's no longer just, is there life? It becomes, what happens if there is? And that's where Europa shifts from fascinating to genuinely unsettling. The ocean beneath Europa's ice isn't a shallow sea. It's a pressure-dominated abyss. If estimates are correct, pressures at the bottom could exceed hundreds of megapascals, far beyond anything on Earth's ocean floor. The water may be salty, perhaps comparable to Earth's oceans, perhaps even more chemically exotic. The temperature near the ice shell may hover just below freezing, but deeper regions, especially near potential hydrothermal vents, could be significantly warmer. That combination, liquid water, energy gradients, chemical disequilibrium, is exactly what astrobiologists look for. But evolution in such an isolated system would follow its own rules. On Earth, life evolved under sunlight for billions of years before complex organisms emerged. Photosynthesis reshaped our atmosphere. Oxygen accumulated. Multicellular organisms eventually appeared. Intelligence followed much later. Europa has no sunlight beneath its ice. No sky. No day and night cycles. If life exists there, it evolved in perpetual darkness. And evolution under those constraints may produce forms we struggle to imagine. Microbial life seems plausible. Complex multicellular organisms. Less certain but not impossible. If hydrothermal systems exist, they could support energy-rich environments similar to Earth's deep-sea vent ecosystems. On Earth, those ecosystems are surprisingly complex: tube worms, crustaceans, fish, all independent of sunlight. If Europa had billions of years of stability, could similar complexity arise? We don't know. And that uncertainty is where the fear lives. Because if we ever send a probe through that ice and into that ocean, we will not just be observing. We will be intruding. Europa's ocean has likely been isolated from the rest of the solar system for roughly 4 billion years. That is longer than complex life has existed on Earth. In evolutionary terms, it is an eternity of uninterrupted development. Earth's biosphere has been shaped by impacts, mass extinctions, atmospheric shifts, continental drift. Europa's ocean, shielded beneath kilometers of ice, may have experienced far fewer disruptions. A stable environment for billions of years could allow life to refine itself in ways we cannot predict. And that leads to a thought most discussions avoid. What if Europa's life is not fragile? What if it is robust? Microbial life on Earth is astonishingly adaptable. Extremophiles thrive in acid, radiation, boiling water, freezing brine, crushing pressure. If Europa has its own lineage of life, it may have evolved defenses against chemical extremes, radiation leaking through ice fractures, or shifts in ocean chemistry. If we introduce Earth microbes into that environment, 2 outcomes are possible. Either they die immediately, sterilized by alien conditions, or they survive. And if they survive, they compete. Biology is not passive, it spreads, it adapts, it mutates. Introducing Earth organisms into Europa's ocean would not just be contamination, it would be ecological interference on a planetary scale. And it would be irreversible. This is why planetary protection protocols are not bureaucratic overreach, they are ethical necessities. Europa is classified as a Category IV body under planetary protection standards, meaning it requires strict sterilization procedures for any land admission. But here's the problem. Absolute sterilization is nearly impossible. Even in clean rooms, microscopic life persists. Some microbes can survive extreme heat, vacuum exposure, radiation. They can enter dormant states and reawaken under favorable conditions. If even one Earth microbe survived the journey and found a niche in Europa's ocean, we might never know the original state of that ecosystem. We would forever blur the line between alien life and terrestrial contamination. And that is the quiet horror beneath the excitement. Europa may represent the most pristine biological laboratory in the solar system, a second experiment in life that ran independently from Earth. If we interfere, we lose that clarity. But there's another layer. Even if we do everything right, even if we design a cryobot that melts cleanly through the ice without introducing contamination, even if we deploy an autonomous submersible into the ocean, what happens if we detect life? Let's imagine we detect microbial organisms. That discovery alone would rewrite biology textbooks overnight. It would confirm that life arises in multiple environments under the right conditions. It would imply that the galaxy may be teeming with microbial ecosystems. But suppose the life is more complex. Suppose we detect multicellular organisms, perhaps simple ones, perhaps something resembling deep-sea life on Earth. That would imply evolutionary pathways that mirror our own in structure, if not in detail. And then suppose, even more unsettling, we detect evidence of intelligence. Now pause there. Is intelligent life likely beneath Europa's ice? Statistically, probably not. Intelligence on Earth took billions of years and a series of improbable events. Europa's ocean may lack the environmental diversity and surface energy inputs that drove Earth's complexity. But improbability is not impossibility, and the mere thought forces a confrontation with something larger than Europa. If intelligence can evolve beneath ice, in darkness, in isolation, then the conditions required for advanced life are broader than we assumed. It would mean that civilizations may emerge in environments utterly different from Earth. Civilizations we could never see. Civilizations trapped beneath ice, unable to reach space. And here is where the real terror emerges. Europa is not just a place we can't go safely. It may be a place that cannot come to us. If intelligent life evolved beneath that ice, it would have no sky, no stars, no awareness of the broader universe unless it developed technology capable of penetrating kilometers of ice. Imagine evolving in a sealed ocean, never seeing a sun, never knowing you orbit a gas giant, never realizing you are part of a planetary system. That is existential isolation on a scale we rarely consider. And if such beings existed, our intrusion would not just be biological interference. It would be cosmic disruption. Even if Europa hosts only microbes, the ethical dilemma remains. Do we have the right to alter an independent biosphere? On Earth, we have already transformed ecosystems. We've driven species extinct, altered climates, reshaped landscapes, but Earth is our home. Europa is not. Europa represents the first time humanity confronts the possibility of interfering with alien life. And that confrontation will define how we approach the rest of the cosmos. But there's still another reason Europa is terrifying. It challenges our understanding of habitability. For decades, scientists focused on the habitable zone, the region around a star where liquid water can exist on a planet's surface. Europa exists far outside that zone. It is nearly 5 times farther from the Sun than Earth. Surface temperatures hover around -160 degrees Celsius. By classical definitions, it should be sterile. And yet tidal heating from Jupiter keeps its interior warm. That means habitability is not limited to sunlight. It means moons around gas giants. Even rogue planets drifting between stars could host subsurface oceans. The number of potential ocean worlds in the galaxy may be staggering, which reframes the silence of space. If life thrives beneath ice, hidden from view, then the galaxy could be biologically active yet observationally silent. We search for radio signals, laser pulses, atmospheric biosignatures. But ocean worlds beneath ice emit none of those. They hide. Europa may represent a dominant mode of life in the universe, hidden, internal, unreachable. And if that is true, then the terrifying part is not that Europa is hostile. It's that it may be normal. A world where life is sealed away, protected from radiation, evolving quietly. And we, surface dwellers dependent on sunlight, may be the anomaly. That possibility shifts the narrative from "can we go there?" to "should we disturb it?" Because once we begin exploring subsurface oceans, on Europa, on Enceladus, perhaps on distant exoplanets, we become agents of change in environments that have never known external contact. Human exploration has always carried risk to explorers, risk to ecosystems, risk to cultures. Europa amplifies that risk beyond Earth. It forces us to confront our role not just as discoverers, but as potential contaminants. And yet curiosity pushes forward. The Europa Clipper mission will soon begin its journey. It will map the ice shell thickness, measure the ocean's depth, analyze surface chemistry, search for plume activity. It is cautious. It does not land, but it is a step toward eventual direct exploration. And once that first drill begins to melt through ice, once that first submersible descends into alien waters, we cross a threshold. Not just scientifically, philosophically, because Europa is not peaceful. It is a radiation-scorched, ice-locked, ocean-covered world orbiting a giant planet that bombards it with energy. It is hostile to human life on the surface. It is possibly alive beneath it. And it represents a boundary between ignorance and irreversible knowledge. We often imagine space as empty, but Europa suggests something else. That beneath the ice of distant worlds, oceans may be waiting. Waiting not for us, but simply existing, unaware of observers, unaware of telescopes, unaware of spacecraft plotting trajectories. And if we go there, if we break that ancient seal, we must be prepared for the possibility that what we find will not just change our understanding of biology. It will change our understanding of ourselves. Because the moment we confirm a second origin of life, we are no longer a singular event. We become one branch among many. And that realization, more than radiation or pressure or darkness, is what truly makes Europa terrifying.